So welcome to today's lesson. My name is Gitonga Peter. I'm a teacher of physics, and I want us to look at the topic electronics. So electronics is a topic that deals with generation and control of electrons. So in electronics, mainly it deals with how electrons are generated and how they are controlled. Then, after controlling the electrons, we look at applications in electronic devices. So during the design production or manufacture of electronic design devices or any work involving electronic design, electronics is a major part to this development. These electronic devices, and this is why electronics comes in mainly, will use semiconductors in order for them to perform. Semiconductors are materials whose conductivity falls in between that of a good conductor. The conductivity of semiconductors falls between that of good conductors and that of insulators. So the conductivity of semiconductor will fall in this case. By this we mean a semiconductor device will at some point behave or become a good conductor, and if some input conditions are not satisfied, it will behave like an insulator. So a semiconductor can be said to be a device that conducts when some input conditions are satisfied. Some of these may be physical conditions like temperature, as we shall see later. Then next, in order for electronics, therefore, we majorly dwell on semiconductors. Let's look at how we come up with these semiconductor devices. To enable us to understand this properly, we shall look at a theory which is called the energy band theory. Energy band theory. Under this energy band theory, it looks at the structure of an atom. I can consider an atom of a substance, an element like neon, which is atomic number 10. Neon will have 10 protons and 10 neutrons, and enclosed in what is called the nucleus of the atom. Protons are positively charged, while the neutrons carry no charge. They are neutral. Then around this nucleus, we shall have electrons moving around the nucleus at different energy levels. The first energy level carries 2 electrons maximum. Then the second one carries a maximum of 8. 3, 4, 5, 6, 7, 8. So this is a completely filled energy level for neon. So these are electrons that will be orbiting the nucleus, held in position by the nucleus force, which attracts the electrons towards the nucleus. Remember, electrons are negatively charged, protons are positively charged. So the attraction between the positive charge in the protons and the negative charge in the electrons creates a resultant force which pulls the electrons towards the nucleus since the electrons are very light, they are the ones which experience the resultant force. Now, back to the energy band theory. These bands, these energy levels or bands, these are the ones I'm calling energy levels or bands, may split further into smaller energy bands. Like for example, this one may split into some other three or into three energy levels, three energy bands. These are energy bands. And this may split into two energy bands. The reason why they are splitting into different number of energy bands is due to the closeness to the nucleus. The one which is closer to the nucleus, this energy level here, will have more nuclear force pulling this band to the nucleus, and therefore it may only split to a few number of bands. As you move further away from the nucleus to this energy level, then you notice there are more energy bands here because the force of attraction between this band and the nucleus is also decreasing. So as you move away from the nucleus, in case you had another energy band here, then energy level, maybe you could see it splitting into even more energy bands like that. So the further away the energy level is from the nucleus, the more the number of energy bands that it may split into. But now, out of the many energy bands that may be formed when an energy level splits, there are only two bands which are important for electrons. So we have seen the energy levels splitting into smaller energy bands, and we have said the number of energy bands formed during the splitting will depend on the closeness of the energy level to the nucleus. The farther away it is from the nucleus, the higher the number of bands. So in electronics, there are two bands which are important. One is the conduction band. So these are the bands which are resulting when at the energy level splits. The conduction band, this one carries conduction electrons. Electrons in this band are ones that take part in conduction. The other important band for electronics is the valence band. So these are the bands that are being formed after the energy level splits. So the valence band carries electrons that are used for bonding. It is important to mention here that an electron which is in the valence band can therefore not take part in conduction. But if it moves from the valence band to the conduction band, the same electron can now participate in conduction. Now this conduction and valence band can be used to give differences between conductors, semiconductors, and insulators. I want us to start with the insulators. Insulators. It's now the energy band theory. We have seen two main bands for electronics, the valence and the conduction band. And those bands are the ones which will determine, or their configuration is the one which will help us to determine whether a material is an insulator, a good conductor, or a semiconductor. Insulators. In an insulator, this is how the bands are arranged. We have the conduction band there, and this is let's have that as a conduction band, this as the valence band, conduction, and this is the valence band. In between, you notice there is a very large gap. This gap is called the forbidden gap, or energy gap. In this material, the valence band is almost electron free. This is almost full of electrons, while the conduction band has almost no electrons. So it has almost no electrons, meaning even if it has, they are very few that they cannot effectively make this crystal conduct. So in order for conduction to take place in an insulator, an electron will have to be moved from the valence band across the forbidden gap to the conduction band. This energy gap is very high, such that if energy was to be supplied to an electron in the valence band to move to the conduction band, then that energy would end up destroying the crystal. By this I mean, if you are supplying energy as heat, then the heat will be too intense that it will end up destroying the semiconductor material. So that makes that material, or it renders that material to be an insulator, and an insulator means the same as a bad conductor, in this case of electricity. Then next, let's look at the two bulbs in a conductor material. In conductors, what happens? If a material is a conductor, then we shall have the arrangement as follows. This is the conduction band, and then the valence band. But instead of having an energy gap, what happens for a good conductor? This will cross over to where we would be having a forbidden or energy gap, like that. On the valence band will also cross over to where we were supposed to be having an energy gap. So instead of having an energy gap, we shall have an overlap region. In this overlap region, the electron from the valence band will not require any energy for it to cross over to the conduction band. So electrons are able to freely cross over from the valence to the conduction band, and that makes this material a very good conductor of electricity. Then let's now come to semiconductors. Semiconductors. In a semiconductor material, the configuration of the bands will just be the same as that in insulators, but with only one difference. The size of the energy gap for semiconductors is smaller. So if this is the conduction, and this is the valence, this is the conduction band, this is the valence band, then this is the forbidden gap. Like you see, the size of this forbidden gap is very small compared to the one we had here in insulators. The one in insulators, we say, if we supply energy for an electron to cross over, that energy will be too much. It will end up destroying the crystal of that semiconductor. But look at the new case now in a semiconductor. The forbidden gap is very small, meaning that an electron can successfully be supplied with energy to overcome the forbidden gap and to move to the conduction bar. So this is what makes conductors conduct when some conditions are satisfied. Like for example, if we heat a semiconductor, if we supply heat to a semiconductor, it enhances its conductivity. To enhance here means to raise the conductivity. But we know for metallic conductors, temperature increases the resistance. But for the semiconductor, temperature increase lowers the resistance. And that is what will make a semiconductor conduct more better at higher temperatures than at lower temperatures. So those are insulators, conductors, and semiconductors. And the difference between the three of them, you see the energy bands, the conduction and the valence bands, as well as the forbidden gap. That is the gap between them. In the conductors, you have seen there is no gap. The valence and the conduction band regions overlap, creating an overlap region between the two of them. And that enables very efficient flow of electrons from the valence band to the conduction band without necessarily requiring energy to be supplied. The next thing now, let's look at semiconductors. Because in the study of electronics, we shall be revolving around semiconductors. This is where electrons are involved. Like we say, in electronics, we are dealing with the generation and control of electrons. So let's look at semiconductors more deeply now. In order for us to do this, we shall start with a small subheading, semiconductors. And then I look at types of semiconductors. Types of semiconductors. Types of semiconductors. There are two types of semiconductors. One, intrinsic semiconductor or semiconductors. These ones are naturally occurring. So these are naturally occurring elements which are semiconductors in nature. They include examples: silicon and germanium. A crystal of an intrinsic semiconductor will have an atom which is neighbored by 4 other atoms and forming complete bonds with them. So if this is a silicon crystal, we shall have an atom forming bonds with 4 neighboring atoms, like that. This is now silicon, 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 silicon. The same case would happen to a germanium crystal. It would still have atoms forming complete bonds with 4 neighboring atoms. So this is now a germanium crystal. It is intrinsic. It is naturally occurring. These are naturally occurring elements which happen to be semiconductors on their own. Then the next type of semiconductors is extrinsic semiconductors. Extrinsic semiconductors. These extrinsic semiconductors are still intrinsic semiconductors to which an impurity atom, so we form these by adding an impurity atom to an intrinsic semiconductor. And the reason for adding this impurity atom is in order to enhance conductivity. To enhance conductivity means to make it conduct even more better. So we add an impurity atom to an intrinsic semiconductor to make it conduct better or to enhance its conductivity. We form an extrinsic semiconductor. This whole process of adding an impurity atom to an intrinsic semiconductor in order to enhance its conductivity so that we get an extrinsic semiconductor, this whole process is called doping. So doping in electronic means adding an impurity atom to an intrinsic semiconductor in order to enhance its conductivity. It is after this process that we end up with an extrinsic semiconductor. Extrinsic semiconductors are of two types. There are two types of extrinsic semiconductors. There are two types of extrinsic semiconductors. These are the P-type and the N-type semiconductors. So types of extrinsic semiconductors. Types of extrinsic semiconductors. The first type, which I call A, is a P-type semiconductor. A P-type semiconductor. A P-type semiconductor is obtained after we dope an intrinsic semiconductor with a trivalent atom. So it's a result of doping an intrinsic semiconductor with a trivalent atom. A trivalent atom is one with three. Tri means three. This one has three bonding electrons. So an atom with three bonding electrons is the one we refer to as a trivalent atom. A very good example here is boron or indium and gallium. But these are enough. So these are the trivalent atoms that shall be used to dope an intrinsic semiconductor to produce a P-type extrinsic semiconductor. Let's see how that process goes on. I will use a silicon crystal. So this is a boron atom. The boron atom has only three bonding electrons. So the boron atom will be able to complete 3 bonds with 3 neighboring atoms, but it will not be able to complete the 4th bond, since it will be lacking an electron to complete that bond. So all these are silicon atoms. These are forming complete bonds with neighboring atoms. But let's look at the boron atom we have introduced. This is the boron atom. Look at how it bonds. It bonds with only 3 neighboring atoms, because it is only having 3 bonding electrons, like we mentioned there. So the 4th bond is not completed due to absence of that extra electron. This is where it now becomes interesting. That absence of an electron creates what we call a hole. A hole which is considered positive. I repeat, the boron atom has lacked an electron to complete the bond with its 4th neighboring atom. That lack of an electron is considered a hole. That hole is considered to be positive. Positive because because a hole is caused by absence of an electron. And like we had seen earlier in the atomic structure, electrons are negatively charged. So the absence of an electron is the absence of negative charge, which is considered positive. So this hole will act as the majority charge carrier. In a p-type semiconductor, holes will be called majority charge carriers. Holes are called majority charge carriers in a p-type semiconductor. We still have a few electrons, some few electrons, which may be thermally generated. Thermally generated means due to the heat, maybe from the surroundings. So thermally generated electrons, which are few, are called minority charge carriers. So in a p-type semiconductor, the holes will move around, or will move. We shall see how they move, forming or resulting to what we call hole current. We have seen holes are considered positive. Current is the flow of charges. So as the holes will be moving, we shall come to see that when we look at the crystal now, in terms of electrons and holes. That flow of holes causes the hole current. These few thermally generated electrons will also move, constituting of what we call electron current. So in a p-type semiconductor, the current that flows is a combination of the hole current and the electron current. I may want to associate this P with the holes here being the majority charge carriers, because the holes are positive. So this and the positive holes are the majority charge carriers. Then the semiconductor is called a p-type. But one thing we should know is that this is not, the whole crystal is not positively charged. The total positive charge is equal to the total negative charge. The fact that we are having a hole here considered positive does not mean that we have a net positive charge. The crystal itself is neutral. Only that holes which are positively charged are the majority charge carriers. And that makes it be called a p-type semiconductor. Let's move to the second type. The second type is the n-type semiconductor. the N-type semiconductor. This is B. N-type semiconductor. This N-type semiconductor is obtained when doping is done. Doping is done by a pentavalent or with a pentavalent atom. With a pentavalent atom. Penta means 5, so a pentavalent atom has 5 bonding electrons. A pentavalent atom has 5 bonding electrons. Now, let's now see how we can obtain an N-type extrinsic semiconductor by doping with a pentavalent atom. I will use, let me give examples of this. A very good example is phosphorus. A phosphorus atom is a pentavalent atom. It has 5 bonding electrons. Let's use phosphorus to dope a germanium crystal. We use phosphorus to dope a germanium crystal and see the result. Phosphorus has 5 bonding electrons, so it will be able to complete bonds with the 4 neighboring electrons and also have an extra electron remaining. That electron will be donated for production. So electrons will now be the majority charge carriers. Electrons are negatively charged, so that's why the N here comes from. Negatively charged electrons are the majority charge carriers in an N-type semiconductor. Then thermally generated holes, just like we had thermally generated electrons in the P-type. Here we shall have thermally generated holes. You can have a hole here, 1 or 2, somewhere. These are the minority charge carriers. So the electrons in an N-type are the majority charge carriers. Thermally generated holes are the minority charge carriers. And the pentavalent atom can be phosphorus, and this pentavalent atom has 5 electrons, so it bonds with the 4 neighboring atoms, and the extra electron is given up or donated for production. Allow me to bring you back here. There is a term that we did not mention. So let me mention it now. This boron atom has 2 names. The boron atom can either be called a p-type impurity, p-type impurity, this is now the boron atom or the trivalent atom, because it may not necessarily be boron. So the trivalent atom, in this case we have used boron as the trivalent atom for doping, can be called a p-type impurity. The extrinsic semiconductor is not pure semiconductor. Intrinsic semiconductor is a pure semiconductor. So this is an impurity added to the pure semiconductor to enhance conductivity. So we call this trivalent atom a p-type impurity, and we can also call it an acceptor atom. Why is it called an acceptor atom? It is called an acceptor atom for accepting to bond with 1 electron less. is body with one electron less. So can also be called an acceptor atom. So if you ask what is an acceptor atom, you will say it is a trivalent atom. Why is it called an acceptor atom? It is because of accepting to bond with one electron less. Let's now come to this pentavalent atom. Pentavalent atom. This one has also two names. One, we can call it the N-type impurity. I wish to write at the top here. The pentavalent atom. So this can be called the N-type impurity. It is an impurity atom introduced to an N-type or to an intrinsic semiconductor in order to form an N-type semiconductor. So we call it an N-type impurity. Another name for this phosphorus atom will also be a donor atom. It can also be referred to as a donor atom. Donor atom because it donates an electron for production. It is donating an electron for production, so it can be called a donor atom. So those are the two types of semiconductors. The extrinsic semiconductors are two types, the P-type and the N-type, and that is how they are formed. The next thing I want us to look at is the p-n junction. The p-n junction. p-n junction. The p-n junction. A p-n junction is formed by doping with both penta with trivalent and pentavalent atoms simultaneously. So we take a crystal, pure crystal, and then we dope it simultaneously with a trivalent atom and a pentavalent atom. The result will be, we shall get a semiconductor where one side will be a p-type region and the other side will be an n-type region. So look at this. This can be the p-type region. This is the n-type region. Resulting from what? From doping simultaneously with a trivalent and a pentavalent atom. In the p-type region, what shall we have? We shall have holes as the majority charge carriers, and we shall have negative fixed ions. In the n-type, electrons are the majority charge carriers, and the holes are the fixed ions in the parent atom. So these are electrons, like that. The electrons here in the p-type are the majority charge carriers. I want us also to include to look at fixed ions. Every electron that moves leaves behind a hole as a fixed ion in the parent crystal. So, in the n-type region, electrons are the majority charge carriers, fixed ions are the holes, and then we may have a few gamma generated holes. These are not holes, these are positive fixed ions. These are just positive fixed ions which are left in the parent crystal by removing electrons, and then gamma generated holes. These ones are the minority charge carriers in the p-type region. Gamma generated holes are the minority charge carriers in the n-type region. The same case happens to this other side. The holes now are the majority. We have negative fixed ions in the parent atom, and then gamma generated electrons become the minority charge carriers. So that is how a p-n junction looks like. But the p-n junction is now this boundary. The boundary between the p-type region and the n-type region is what we call the p-n junction. So as this happens, holes will flow from the p-type region, where they are the majority charge carriers, to the n-type region. Consequently, electrons will also flow from the n-type region towards the p-type region, where they are majority in the n-type region. So they will move towards the p-type, and the holes will move from where they are majority to the n-type, that is p-type towards the n-type. So as electrons and holes cross over, we are going to leave a region here of uncovered fixed ions. Let's go back to the fixed ions. This is a positive fixed ion covered by an electron. Another positive fixed ion in the parent crystal covered by an electron. If we go to the p-type side, we have a negative fixed ion covered by a hole. This is a hole covering the negative fixed ion. So let's now look at what will happen if we have this exchange of electrons and holes. We shall reach a point where we shall have no charge to cover some of the fixed ions on either side of the p-n junction, due to depression of charges. As charges continue flowing, there will reach a point where we shall lack charges to cover the fixed ions in the n-type region and those in the p-type region on either side of this p-n junction. That one alone creates what we call a depression layer. Depression layer. It is being created by depression of charges until some fixed ions are left with no covering charge, like these ones. So these two will have no covering charge because the electron here has moved away, the hole here has crossed over, so these ones are left with no covering charge. That region on either side of the p-n junction of uncovered fixed ions is what we call a depression layer. So let's look at the depression layer itself. We now look at the depression layer. The depression layer. This is a layer where charges are depleted and we are left with fixed ions that have no covering charge. That's the p-n junction. This is the n-type region. This is the p-type region. We have seen in the p-type, as holes move, we are left with negative fixed ions, sorry. These are negative fixed ions. Negative fixed ions. Each of these negative fixed ions requires positive charge to cover it, like that. Then in the n-type, it is holes, which are the fixed ions. Every hole with a negative covering charge. Then again, other holes here. Each of the holes is supposed to have a negative covering charge. But I want us to look at these two negative fixed ions in the p-type region and these two positive fixed ions. These have no covering charge. This is what I'm calling a depression layer. So a depression layer is a region of uncovered fixed ions. If you ask what is a depression layer, it's a region of uncovered fixed ions on either side of the p-n junction. Ukumbuke p-n junction tumeona ni boundary between the p-type and the n-type region. This line is the p-n junction. So the depression layer will be on the right hand side and the left hand side of this p-n junction. That region of uncovered fixed ions on either side of the depression layer, of the p-n junction, is what we call the depression layer, caused by depression of charges as holes diffuse from the p-type to the n-type region and as electrons diffuse across the p-n junction from the n-type region to the p-type region. These are electrons. So that depression of charges will result to us having fixed ions with no covering electrons in the n-type, as well as negative fixed ions with no covering positive holes in the p-type region, creating what is called a depression layer. That was our lesson for today. When we make another video, we shall be looking at how to overcome this depression layer, because when this is created, when the depression layer is created, it creates a very high sort of electric field such that holes in the p-type cannot be able to move to the n-type. So this is a sort of an electric hole, which we call a potential barrier, an electric field. This is what I'm talking about. Here in quotes, that depression layer creates a sort of an electric field, preventing holes from moving from the p-type region to the n-type region, as well as electrons from diffusing from the n-type region to come to the p-type region. So that hill creates a potential barrier between the p-type and the n-type region. This barrier has to be overcome in order, or makes this depression layer not allow any further diffusion of charges. In other words, the semiconductor crystal cannot conduct when there is this depression layer, because we have seen there can be no diffusion of charges across the p-n junction. Now, this electric hill has therefore to be overcome. To overcome that electric hill, we have to get rid of this depression layer. To get rid of this depression layer, we shall provide voltage across that crystal. That process of supplying voltage to a p-n junction is called biasing. So through that process of biasing, we shall be able to provide enough voltage that will overcome this potential barrier and that will make this p-n junction start conducting again. So in the next video, we shall start from biasing. We want to see how biasing is done. How do we bias a p-n junction to remove this depression layer? Otherwise, thank you very much for today. My name is Gitonga Mwangi. I'm a very senior teacher of physics, and I welcome you in this journey. Thank you very much, and have a good evening.